Alright, this is the start of a two-part video that's going to be talking about three very unique vectors that have to do with parametric curves. And I'm just going to say them right now and then we'll go through them. So one is going to be the tangent, the unit tangent vector. That's always going to point tangent to the curve. Just like you might think a 2D derivative points tangent to the curve, but this is actually a vector value that points tangent to the curve at some given point. Now, the second one is called the normal, the unit normal vector, and what that represents is a normalizing force. So, when I stand on the ground, gravity's trying to push me down. Well, because I'm staying up, there must be a normal force that the floor is applying on me. So imagine if you were to take a bank turn on a roller coaster. Which direction do you think the normal vector would point, the unit normal vector? So it actually points towards the center of the radius of your curvature. So because your body wants to fly off the roller coaster, but the walls are holding you in, there's a normal force that's holding you in. So that's the unit normal vector. And then there's one called the binormal vector that's important, but not nearly as important conceptually, that we'll cover in next video. So here we have a parametric curve. I have the time in integers of half pi, and so the curve is my vector curve. R of t is equal to, for the x component it's cosine of t, for the y component it's sine of t, and for the z component it's just t. And so when t equals 0, I plug in my values and I get the point, well, not the point though, the vector 1, 0, 0. When I plug in pi halves, I get the vector 0, 1, pi, and pi is negative 1, 0, pi, 3 pi halves, 0, negative 1, 3 pi halves, 2, and 2 pi is going to be 1, 0, and 2 pi. You'll notice that the x and y went through a transformation, but by the time we got to 2 pi, we ended up with the same values for x and y. And that z just continually grows with time. And so what we're actually looking at here is a spiral. I've marked the points t equals 0, t equals pi halves, pi, 3 pi halves, and 2 pi. And you can see that it sweeps out a spiral that is constantly growing at one velocity in the z direction, while having some sort of normalizing force holding the path inwards towards the center. So let's take a look at let's take a look at when t equals pi halves. Here's our vector r, which is r at time pi halves. So r parentheses pi halves. And now the question is, what is something that is always parallel to direction? In other words, our direction r. What is something that's always going to be parallel to this line at that given point? And the answer is velocity. So velocity always points in the direction of motion. Not always true with, say, acceleration, but for velocity, velocity is always tangential. That's part of the definition. And so if r is our position, now we know that our position, if we take the derivative of our position with respect to time, that we get a velocity. And so we're going to exploit that dr dt is v, and that v is always parallel with the path of travel. It's always tangential. And so, for example, in this, for dr dt, we will take these component by component and take the derivative of each component with respect to t. So cosine of t for the x component, the derivative of cosine of t is negative sine of t. The component for the derivative of sine of t is going to be cosine of t. And the derivative of t is just 1. And that makes sense because we agreed that z was growing constantly. And so if z is growing at a constant velocity, it had better not have any acceleration. Whereas things moving in a circle always have centripetal acceleration. So for the x and the y components, it makes sense for us to have t and not just a constant velocity. So here is our velocity vector. It will always be parallel to the surface of the curve. It's always going, or not to the surface, it's always going to be tangent to the curve, no matter where the curve's at. But like I said in the last video, all vectors originate from the origin. And so even if we're looking at t equals 1/2, right, we might have a tangential velocity pointing in this direction, but because of the way vectors work, technically the velocity vector is on the origin. But what we do for our own mental health is we take that velocity and we move it in our minds just to make it lie where we think it should. But in actuality, all vectors come from the origin. I just wanted to make sure that that's clear. All right, so now that we have velocity, how do we get to the unit tangent vector? Well, we know velocity is tangent, so we have the direction part good. Next, what we need to do is make it a unit vector, right? So we have to normalize it, make it length 1. And in order to do that, you'll remember that we would take the vector that has the intrinsic direction of the tangent, and we'll divide it by the magnitude of the vector. And that's going to give us what I write as a big T with the unit vector hat on it. So that's the unit tangent vector. It's velocity over the absolute value of or over the magnitude of the velocity. And so there is the unit tangent vector. Let's go ahead and move on to the unit normal vector. All right, so the tangent vector is here. I'm going to have to go ahead and erase my r vector to make some more room. The normal vector is going to restore motion. So in other words, we're going to need to have some normal vector pointing in this direction. And if there is no tangential acceleration, it's actually interesting what that will be. It will actually be acceleration. So unless there's any tangential acceleration, in other words, centripetal acceleration doesn't count here. As long as there's a constant velocity that's tangential, acceleration will always be pointing towards in the same direction as the normal. So what we could say there is that the normal vector, the unit normal vector, is equal to acceleration divided by the absolute value of acceleration, which of course is the derivative of velocity to find acceleration. And so you could, but technically there's a loophole here to where this wouldn't work, and that loophole is if any tangential acceleration exists, this formula won't work. Which is frustrating, because when you think about it, if there's just centripetal acceleration, it's always pointing in the normal direction. But the second you get tangential acceleration, now this isn't pointing always 90 degrees from velocity. So how can we fix that? Well, we know that the derivative, for example, of the unit tangent vector with respect to time, that's going to find just the acceleration centripetal, because if we're looking at just the tangential velocity and we take a derivative of that, we're just going to get the acceleration that's pointing in the centripetal direction. So the area, the acceleration that's pointing towards the center, and we're going to be excluding any tangential acceleration that may exist by using this. And so to make it a unit vector, though, we have to divide it by its magnitude. So the magnitude is the change in the tangent vector, unit tangent vector with respect to time. And that's going to always be our normal vector. So this is the better equation because it works all the time. Because we're only dealing with the acceleration centripetal in this case. Whereas with this case, if this was speeding up along its tangential velocity, then we'd have acceleration that we couldn't account for with this equation. I just wanted to show you the logic of how we're using acceleration to figure out our normal vector. And so at that point, I would say we have a pretty good knowledge for the unit normal and the unit tangent vector. And in the next video, we will talk about curvature, which is represented as the symbol kappa. We'll also talk about radius of curvature and a couple of planes and the binormal vector. So I'll see you next video. Thanks.